Okay, well, we might kick off. Welcome to everyone that's here. Thanks for joining us this evening. My name is Michael Murphy. I am a co-founder of the Builders Declare movement. We're actually up to webinar number 17 today, and the topic for tonight is reaching 7 stars and beyond. We've got a very special guest in Jeremy Spencer here tonight from the company Positive Footprints. Before I get into that, I'd just like to say a big thank you to our sponsor for tonight, who are Maxa Design. They are maxadesign.com.au. They work with some of the builders in the Builders Declare movement, and we'd like to thank them very much for sponsoring tonight. I'd first like to begin by acknowledging the traditional owners of the land in which we meet. I'd like to pay my respects to elders past, present and emerging. I'd just like to do a little bit of an intro for Jeremy and Jeremy's company. Jeremy is a long-time builder. He's a thermal performance assessor and a co-director of Positive Footprints with his wife, Chi Lu. It's a design and build company. Positive Footprints is a multi-award winning construction company dedicated to making high-performance sustainable homes and renovations easy to achieve and affordable. Positive Footprints has worked for the last 2 decades to show that energy-efficient design and high-performance construction is a cost-effective option and that can be a mainstream reality. Jeremy is a founding member of Builders Declare. He currently sits on the Design Matters National Board. He's a NatHERS stakeholder committee member. He's also an annual judge at the National Sustainability Awards. So a very experienced person. He's an educator who's also previously been on the Master Builders Green Living instructor team. And Jeremy's very passionate about spreading the message for environmentally sustainable net zero carbon design. So we're about to kick off. Before I get into that, a quick disclaimer. The information that you're about to receive is based on the experience of presenters and may not necessarily relate exactly to your situation. So if you'd like any specific questions, please just reach out on the chat or via email. Tonight's webinar will be around about 45 to 50 minutes, possibly a bit longer, depending on how we go with questions. I'd like to encourage everyone to reach out if you've got any questions, just to type them in the chat, and I'll get to them as soon as I can. We'll probably try and save most of them for the end, so Jeremy can work through his presentation. So with no further ado, I will hand off to Jeremy to start his presentation. Thank you very much, Jeremy.
No problem. Let me share. Let's see if this works. Can you see that screen at the moment?
Yes, we can, I believe. Can maybe perhaps in the chat, just let us know that we can see Jeremy's screen.
All right, I've maximized it, just checking you can see it now, and then we can get going.
Great, we've got a couple of yeses in there. And as we're going along, feel free to type your questions in that chat and I will collate them for the end of the session or during.
Beautiful. All right, well, thank you. Thanks very much, Mike, for the introduction. Thank you again, Maxa Designs. You're a great team. And thank you everyone who's logged in. I hope that I can give you some value for the next hour or so. Now, what I want to cover, I've got a little bit to go through, so be patient with me here. But I want to go through the upcoming changes to the NCC. That's the 7-star whole of home requirement for new homes. So I want to look at that. I want to look at where the building industry is going, at least the residential building industry, where we're going over the next 10 years, what the changes are likely to mean for you guys watching as well. And I've run my house through one of the new whole of home tools. the Sustainable Victoria version, which is the first tool off the ranks to be working. So I want to show you that as well to let you get a good idea about how it might all work for you. And then I want to focus on the 7-star part of that 7-star whole of house. That seems to me, talking to a lot of people in the industry, that seems to be the part that's causing a lot of angst in the industry. I'm not so worried about having to put in appliances. Okay, people can do that. People are worried that their plans won't get to 7 stars. And they've got a bit of a right to be worried, because going from 6 stars to 7 stars is not the same as going from 5 stars to 6 stars. 5 stars was such a low bar. They really didn't need to change how you did anything. You would just do your plan, give it to the thermal assessor. If it didn't already get to 6 stars, they would then maximize insulation in cavities. If it still didn't get there, double glazed windows, that'd get it over the line and hand it back. And so no real change there. But to go to 7 stars, well, now we're talking about insulation and insulated windows. That's not necessarily going to be enough. We need to reach for other tools. At the moment, it's a little bit like we're just solving things with a hammer, but in the future, you've got other tools in your tool belt that you're also going to have to grab to get to 7 stars. I'm not saying it's hard, but it's like hanging a door. You can't just hang a door with a hammer. You need your chisel, you need your drill, you need other things. It will seem very hard if you try and do it with a hammer. So I'm arguing, I guess, that increased specification is not the way to get there, not the way to get there cost effectively anyway. All right, I want to start though, let's look at the where we are in the world and where the building industry is. This is the carbon dioxide impact, the emissions for the world that you're looking at. A couple of years old, but nothing's changed. We're still on this upward slope, 36 billion tonnes and counting. And this is the graph that has convinced a lot of countries to change or to declare net zero by 2050. This, and obviously the climate change that the carbon dioxide buildup is causing. Our country as well is in that mix. And what that means is that every industry within those countries, building industry included, will need to find a way to remove the carbon dioxide burden, or to move away from fossil fuels and to become a zero energy industry, or a zero carbon industry, I should say. Now, the building industry, if you look over there on the side, 39% of that 36 billion tonnes is related through operational energy use and embodied carbon within building structures. 39% is related to buildings, which is, that's a huge amount, obviously, almost disproportionately so to the building industry. And what that means is that the onus is on the building industry to roll up their sleeves and get on with the job of trying to flatten this curve, because without the building industry getting involved, it's not going to happen, basically. The good side of that is that if you're in the building industry, you are in a position to make significant change, a disproportionately big role that you have. So what you do in your business matters. What you do day to day does matter. All right. Now, each industry needs to create a roadmap to get to a net zero industry. And the building industry actually already has that roadmap ready to go. It's called the Trajectory for Low Energy Buildings. And this tackles operational energy use. And it's actually came out in 2019 when the then heads of state under COAG got together and signed it off. And it sort of slipped in a little bit under the radar because it's quite an ambitious document. I know people pushing at the time, they were pushing really hard, but for the wider industry, not all that many people know about this document. It's worth a read. It's only short, but if you read it, you will understand completely why we've got the proposals that we've got into the NCC. So if we look at the trajectory itself, it actually gives a timeline for the next, well, up to 2030. And it has a number of iterations along that timeline of what's going to happen. But I just want to, I don't want to go through each one of these things, but I'll go through the very last one. So I'll just move my thing so I can read my screen. This shows you where we're heading. We're heading to zero energy and carbon ready buildings. That's residential, commercial, and existing as well is covered under the trajectory. And a zero, I'll read out what it is. A zero energy and carbon ready building have an energy efficient thermal shell and appliances and have sufficiently low energy use and have the relevant setup so that they are ready to achieve net zero energy and carbon usage if they're combined with renewable or decarbonised energy systems on-site or off-site. So this is where we're heading. This is the roadmap. This is what the ABCB Building Codes Board is working towards. And what that is a building that has an energy efficient shell. It's got energy efficient appliances such that if you put PV or another renewable resource energy on the roof or close by, that house will be operating in a net zero way. That is producing as much power over the year as it's using. One other thing to point out under 2022, let's see what the proposal was for 2022. And it says, introduce an energy and carbon usage budget for residential buildings that includes appliances already covered in the NCC, hot water, pool pumps and lighting, adds a new requirement for space conditioning, increases thermal energy efficiency requirements and allows for additional energy performance through on-site renewable energy. And that sounds familiar because that is exactly what we've got. This is the proposal under the NCC, and the proposal is increase the energy efficiency going from 6 stars to 7 stars. That's one part of it. And the other part of it, the whole of house part of it, is to start including the major appliances covered under the NCC. So we've got heating and cooling, lighting, pool pumps, hot water, and then on-site energy generation to throw into the mix. And the way that this is going to work, you have to get to the 7 stars. That's going to be a minimum for the thermal shell. But within each one of these appliance groups, they will specify a standard appliance. They're calling it a benchmark appliance, reasonably efficient. And what you'll need to do is you need to specify an appliance that is at least as efficient as that benchmark. However, you're allowed to trade off a little bit between the different appliance groups. So you can have one that's a lot more efficient in one area, less efficient in another area, as long as, on average, when the simulation does its little workings in the background, the whole house is above the benchmark. The other way you can do it is if you're a bit below, you can put on photovoltaics on the roof to bring it up above that benchmark. And so that's the proposal at the moment. We don't know exactly what's going to get through in this terms 2022 NCC, nor do we know if there's going to be a transition period. I would say there's going to be at least 12 months. That's my gut feel, if not longer. And if there is a transition period, by the way, that's a great opportunity. If you're involved in design, you should be using that transition period to make sure that all your designs are starting to get over that bar of 7 stars easily in that transition period, so you can hit the road running when it starts. This is the First Rate 5 whole of home portal in the cloud. And I've run one of my projects through it, so I just wanted to quickly show you what a whole of home software would look like. So this takes the thermal performance software, the First Rate 5 file. So you start by doing a normal energy rating as per normal. And at the moment, it only interacts with First Rate 5, though I think that will broaden out to all the NatHERS software later on. But you get, sorry about that, but you get your First Rate 5 file, you upload it into the tool, and then you are met with these screens that ask for some more information. They ask for, starting off, heating appliances and cooling appliances, and what capacity and what energy rating or star rating. And you can put in, also you can look in the specifications and put in COP ratings and a few other ways of entering the data, which the tool tells you. So that was heating and cooling. We use, in this particular job, we use efficient reverse cycle air conditioners. Then it also asks about fixed appliances, cooktops and ovens. Now, I should just point out that under the 2022 NCC proposals, cooking is not part of it. However, under the trajectory, it does mention adding other modules later on. So my guess is that the other modules that are likely to be added is cooking, probably pool heating as well as pool pumps. We've got pool pumps in this one, but maybe pool heating down the track because that uses a lot of power. And also when car charging becomes a thing and we get more electric cars, my guess is that that will possibly come under this as well. But at the moment, you can put in cooking in the Sustainability Victoria pilot tool. And so I put an induction cooktop, an oven. This was an all-electric home. For the water heater, heat pump water heating, high efficiency. For plug-in appliances, you don't get to interact with that. That's things like TVs, computers, anything that plugs in. The software will just assume, depending on the size of the house that you're doing and the number of bedrooms that comes from the thermal model, it will assume a certain plug-in appliance amount. What you can do though, you can put in what your heating, not your heating, what your lighting watts per square meter is. So that's an easy way to get points. You can call up 3, 4 or 5 watts per square meter. So designers, it might be a good idea to start making sure that you have a lighting schedule on your plans if you want the energy rater to be able to input that. And the other thing obviously that's going to change as we do this is designers, you're going to need to make sure that you know what heating and cooling, what hot water, you're going to need to know a little bit about appliances. So there is a bit of education, obviously, to go into making this work. Thermal performance assessors, you're going to need to know even more, because when a rating doesn't get over the requirement, obviously they're going to ask you, well, what are my options? What should I look at? Any thermal performance assessors, you might want to start looking at heating and cooling in the industry and what's around and what's efficient and what's not. Paul,
can I jump in really, really quickly, because I feel like this question is just relevant to the topic.
Yeah, go for it.
Tim Forsey has asked a question. So a home with gas can still pass. So a question about whether or not gas, from a regulatory perspective, will be mandated to go out or not with this.
All right. So yes, this is fuel independent. It's not promoting any particular one. And at the moment, gas is still reasonably efficient compared to other ways of doing things. Our electricity grid is still reasonably dirty, and especially down south where we are in Melbourne, in Victoria. Other states are more ahead. So in some states, as the grid greens, gas will become less and less a performer on this particular software. And we're really, as long as whatever you do gets over the line of the standard appliance, then it is okay to use at the moment. And so, yes, you can use gas.
We might revisit that topic later and talk about all electric homes and what we would perhaps suggest there, but we can perhaps revisit that later. Thanks, Jeremy.
Yeah, there are definite benefits to going all electric. And as the grid becomes greener and greener, gas won't be able to become greener and greener, and it will become more and more obvious which is the environmental choice there. Okay, pool. Is there a pool? There wasn't on this project, but if there was, you get to put in your pool pump. And on this project, there was 6.3 kilowatts of photovoltaics facing east and a bit facing west. There was no north roof, in fact, on this. Okay. You then press calculate. It does its calculations in the background, and you get a screen a little bit like this. And what it shows is the energy production. If you look along the bottom, along that graph down there, you can see in the column graph, that's each month of the year. We've got two columns. One is the dark green, that shows the power being produced by the photovoltaic system. The coloured column is the power being used by the house. And you can see that this particular house, and you can see in the centre up the top there, you'll see it's 7.2 stars. So this was actually on a very tight site, very solar constrained, but we got it to 7.2 stars. But even at 7.2 stars, it's just with a 6.3 kilowatt system, we're producing a lot more power than the house is using because it's stocked with very efficient appliances. And up in the left, you can see a summary. You've got this house draws electricity from the grid, and in doing that creates 3.99 tonnes of carbon dioxide. but it's also putting green electrons out into the grid for neighbours to use. And in that sense, it is offsetting 7.27 tonnes of carbon dioxide for a net emissions of -3 tonnes. So basically the grid is 3 tonnes better off from a carbon point of view for having this house on it. It also, the software can also break down the different areas where the energy is being used in the house by energy use, emissions, and annual energy costs as well. So what I can really see with this tool and the benefit of it is it will answer the question, first of all, for the homeowner, how much photovoltaics do I need to put on my roof to break even? That's a pretty useful question. It will also, for the savvy builder, allow a point of sale sustainability upsell. You might say, well, you know, we could put on a high efficiency heat pump hot water system, and you can show how much you would save from doing that and say, well, it's going to cost $2,000 extra compared to this cheap one, but you're saving $400 a year. And you can run those simulations. Or you could say, you know, should I really go for those triple glaze windows? Let's run a simulation, a thermal simulation with double glaze and triple glaze, put it through the software, see what the difference is. So yeah, it's useful. The other thing that I think that this software does is it makes sustainability or energy efficiency visible in a way that it hasn't been visible in the past, which is really good. Potentially, project homes could be taking this and they could be putting up a sticker and saying, you know, this house is predicted to be X to run, a little bit like when you go and you buy a car. So useful, good tool. It does, for builders in particular, I think this movement to high performing or marketing high performing or promising high performance comes with some risks. It comes with the risk that you've promised a lot to the client and then the house doesn't perform. And we all know there's a big difference between an energy rating and the house performance on the ground, and it comes down to build quality, which is something that builders declare bang on about all the time. So I'd really suggest that any builders watching this, it's really worthwhile, if you haven't already, get yourself a blower door test, do a blower door test, see how tight your homes are. Get a infrared camera. You can get cheap ones that go, well, not cheap. They're not cheap, but they're definitely worthwhile. But a little attachment goes on your phone and straight away you can see how well your insulation's being put in, where you're losing heat, where the issues are. And it doesn't take long to upskill a team until you've got a team who are installing and doing the build so that it performs like it should, like the energy rating says it should on the ground. So that's just a little heads up for the builder. The heads up for the designer, of course, is you don't want to, and for the thermal assessor, you don't want to be in this position where you've done a design, you've put it through town planning, you've done engineering, you know, so much time is going, it could be 2 years going through council. And then you go to get a building certificate. They say, get a thermal performance report. You go to the TPA, the thermal performance assessor, and he hands it back and says, this won't get to 7 stars, right? Because it's too late by that stage. So now I want to look at using passive solar design to achieve 7-star plus performance. This is the tools and the knowledge that you need to know as a designer. You definitely need to know it as a thermal performance assessor. And thermal performance assessors, I would suggest, need to let designers know that change is coming, and designers might want to start, if they're not already getting 7 stars, they might want to start giving their plans to thermal performance assessors at design stage so that they can get some early feedback. And thermal performance assessors will need to understand passive design well so that they can do improvement reports and listing, you know, how this house performs and how it can perform better at that early stage while the design's still fluid and you can make changes to it. And, you know, for builders as well, this information is really, I think, is foundational at this point in time in the building industry. All players need to know it. So we're all talking from the same hymn sheet. So we're educating clients in the same way. And so the builders aren't wasting time doing costing and on designs that will never get there. you know, and wasting their time. So good information for everyone. Passive solar design. So what is it? It is simply climatic design. It's simply designing a house so that it uses the energy relative to the site to, in the first instance, provide the heating and cooling. So that's the sun for heating, the wind for cooling, the earth for maintaining stable temperatures. Tries to use those. And then, of course, it does have space conditioning, but I like to think of the space conditioning more like a booster on a hot water system. It's just something you put on and it will come on when the climatic conditions aren't enough to have the house at a stable temperature that we like, at 20 degrees or so. Now, as you can see down the bottom with Australia, there's lots of different climates in Australia. There's two, and there's a little bit of tweaking of passive solar design for all those different climates, but there are two overriding strategies. One is what I'll be presenting today. The other one is in Northern Australia. So basically in the southern half of Australia, we're trying to heat the home for most of the year, or for a lot of the year. It becomes a little bit less as we move up. But the rules that I'm going to give you today work well pretty much anywhere from, you know, the bottom of Tasmania up to Brisbane. If you go above that, you're really into zones that you're just wanting to cool all the time, not get the sun in, shade it out, and work with prevailing breezes and potentially the mass of the earth if there's a large diurnal temperature swing. So I'm not talking about that today because I've only got a certain amount of time. However, the invitation is open. If there are any designers or builders in the tropics who want to present on that, that would be an awesome resource for the industry. In which case you should contact us. All right. Before I get into the actual rules or those tools that I was talking about, I just want to start at what we're looking at as far as the benefit here. So this here is, you've probably seen, if you've seen presentations I've done before, you've seen me use a pie graph. This is the pie graph for Australia. In the past, I've often just used Victoria. And the pie graph for Australia, the space conditioning is a little bit smaller because it tends to have a bigger wedge of space conditioning in colder states and a bit smaller in the warmer states. But this is an average. If we took an average of all the Australian homes, new and old, averaging them together, this is how the energy split happens in the home. The average home is about 200 square meters. The average energy that gets drawn to provide the services in the wedges contributes about 6 tons of fossil fuel burning to provide that energy per house per year, and has a combined energy bill of 2,242 when you add gas and electricity together. So 6 stars. 6 stars is approximately there. So a little bit less than a quarter of the wedge, maybe about a ton of carbon saved on the average home by going 6 stars. That's, of course, if you also get the building built to 6 stars. But that's why we had the 6 stars. It does do something. And now we're planning to go to 7 stars, which is a bit over a quarter, heading on to about a third of the pie there. But of course you can, that's again going to be the minimum. You can go further and quite easily. And I do want to get across that 7 stars is like 7 out of 10. That's like, it's like a B on a test. It's a B on a test. 6 stars we'll say is a C. This is a B. If you get higher than that, you might get to an A or an A plus. So we're talking a little bit of effort, not a huge amount of effort. If you do put a bit more effort into the design, 8 stars, 9 stars and 10 stars if you can go all the way. And that's a decent saving. But you can see with this, if we get to 7 stars, that there's still a lot of the energy pie left, if you like. And that's where whole of home really comes into its own. In fact, of the 2 parts of the changes to 7 stars and whole of home, by far whole of home is the most important one we really need to get behind as an industry. Because if it's the appliances that use the energy, and if we can put in efficient appliances, you really cut into each one of those segments significantly. And like you saw before, if you put on a reasonable size photovoltaic system on the roof, then you can get to net zero reasonably easily. All right. So that's a little bit of background. Let's get into the secret to 7, 8, 9, and 10. All right, there are 5 rules. I like to think of it as 1 rule for each finger, just to make it easy. And they're all surprisingly easy rules. It's really just having the confidence that, yes, I do understand this tool right, and applying that to designs, or applying that when you're assessing plans to get a sense of how this is likely to rate up. So the first rule is orientate to north. The sun rises in the east and it sets in the west, but it doesn't go directly overhead, as you can see in the picture, because we're in the southern hemisphere, or most of Australia's, well, Australia's in the southern hemisphere, most of Australia's below the Tropic of Capricorn. So the sun will be on the northern part of the sky as it travels from east to west. And then in winter, it's lower in the sky. In summer, it's higher in the sky. Now, we can use that, obviously, if we put the important rooms on that north side of the home and appropriate windows, we should be able to get winter, whenever the sun's out, we should get, you know, almost 12 hours of heating through the winter when the sun's moving across the sky during the day. And with the right sort of eaves, we should be able to keep it out. So this is really our first resource, is the sun. And I want to show you how I think through the process by taking you through, I guess, how we think about it in our design team here. So we start off by putting the block. Now, this will be the quintessential passive solar layout. There's nothing on the north in this one. There's no overshadowing. It's sort of the perfect conditions. But I'll show you how I think about things. First of all, I put on the sun diagram. And you'll notice here that we've got blue and we've got red. Now, the sun doesn't always rise in the east and set in the west. In fact, in winter, the depths of winter, it will rise in the northeast and set in the northwest. And then in summer, when the days are longer, it will rise in the southeast and it will set in the southwest. Now, we can use that fact. The other thing that we put on the plans is the prevailing summer breeze. So breezes are pretty much only useful, the ones that might cool you down in summer. So they're usually either in the afternoon or in the early evening. Those are the sort of breezes in summer that you're wanting to put on. I'll show you later how to find those breezes if you don't know where to look for that information. But I start off by putting the living areas on north. Now, why the living areas? The living areas because people are in those for a long time during the day, many hours, and then even once the sun goes down, they're in them for many of the evening hours as well, you know, maybe going to bed 10, 11, 12 o'clock at night. So they get a lot of use, those living areas, and we want them to perform well through all that time. So they get priority. Put the living areas on the north. Kitchen, I like to link it with the living area for that sort of open plan look, but putting it on the south there keeps the sun off the food. Also, it allows me, in this particular setup, I can put some windows in the south on the kitchen, some windows on the north on that living area, and I can get some great breezes blowing across the living spaces where people are going to be in summer. Kids' bedrooms, so I put them at the back of the house for a bit of privacy. But the other reason I put it there is the sun sets in the southwest in summer, and that last bit of sun is very, very low in the sky, very hard to shade out with any eaves. So it's not bad to have a bit of building in the way to protect the living area. So I sort of think of that kids area or sort of like a thermal buffer, if you like, from that last oomph of energy on a summer's day. Now, of course, that's not so nice for the kids' bedrooms themselves. So trying to have the windows too big, and you might also think about planting trees or something in that southwest corner there. Master bedroom at the front, common setup, separated from the kids, give a bit of privacy, watch the comings and goings. I had one more space on this block to put a north room. This is a single story one. So we put the master bed there, and the garage then goes on the south, on the front, so the car can come in. But the other reason we put it there on the southwest is the sun rises, sorry, on the southeast, the sun rises on the southeast in summer, in the morning. And really you want to delay in summer, you want to delay the house heating up. So it's good, again, that room or that garage is used as a bit of a buffer there. Utilities on the south, laundry, bathrooms and so forth. Colder areas that you're not in for very long. And that's pretty much it. That's pretty much the quintessential layout. And you can sort of see that the rooms are, I like to think them almost, these rooms on the south, almost as buffers or extra insulation for that living area, which gets pride of place. And there's a floor plan. This is one of our Carbon Zero floor plans. It's 8 stars, but it's not perfect, you know. You can see that we've put in a courtyard here. But this courtyard wall, it actually, as the sun rises in the morning in winter, this part of the house is actually shading the sunlight getting into the living space. But this still gets to 8 stars. All right. So my point here is that you don't have to be perfect. It doesn't have to be a flat side. That would be better thermally if it was flat all the way along there on the north. But you know, we want to space things off to give that outdoor deck a nice space and not have it too close to the boundary there. So like I said, we only have to get to B. 7 stars is B. If you want to get to 10 stars, then yes, we have to tick every single rule. But as I present these rules, it's not necessarily to do all of them 100%. If you get most of them, most of the way, you'll get to 7 stars. If you get if for one of them you can't get, you know, you don't have a good orientation to the north, you can only look to the south, well, will start to raise a bit of a red flag for you. Hey, I better make sure that I nail the other rules that we'll come across. So I just like to think to myself, this is a thought process that goes through my head when I'm looking at plans and looking at my plans that my partner Chi Lu does. Are my living areas getting north sunlight most of the day in winter? That's it. Doesn't have to be all the day, most of the day. If I can answer that then with a yes, then I think I'm on the right track. If I can also see other rooms that are also getting north for most of the day in winter, then that's a big tick. There's, this is just, well, here's a render of the house. The 2 things I want to say about this. First of all, notice that I've put a space dedicated to solar panels. That's just an idea, but photovoltaics are now such a cost-effective option, and electricity is such a useful thing to generate in the house and to share to lots of different sources and appliances and functions, that it's not a bad idea to start thinking about in the design and making sure you've got enough roof space for the photovoltaic array that you're planning to put up there. The other thing I'll say about this is that the rules that I'm showing you are look independent. So we just like this particular look, but you could go for any style, obviously, as long as you're sort of using the rules. It doesn't have to look like a positive footprint home. This is the inside of that particular home. It's shaded at the moment, but in winter, the sun will just come in there, heat the concrete, then the good insulation, the good windows will keep that heat in the house throughout the evening and delay the need for heating and cooling to come on. Now, the other sort of rule of thumb, or the other way that I think, especially when I'm looking at other people's plans in particular and assessing them, plans that just come across my table, I will ask this question: can I work out which direction is north just by looking at the elevations? And these are the plans for, or a draft set of the plans for that particular house. And you already know that the top one is north. But if you're looking at plans and you think to yourself, oh, that top elevation, that's got to be the north one, right? Now, if later on you go and you put on the directions and this wasn't north, if that was south or east or something else, well, again, red flag. Doesn't mean that the design will fail the 7 stars, but means that you're going to have to hit the other rules pretty hard. All right, so that was the easy scenario, north to the side. That's the easiest. Now, I just want to show you one of what is potentially the hardest direction to get a good score on, and that is north to the street, because theoretically we would want to put our living spaces close to the street, nice big windows, but most clients don't like that. Most clients don't like the idea, the privacy issues that imposes, and potentially the security issues as well. So I'll just show you, I won't go through the whole bubble diagram, but I'll just show you a way that we solve this in the Carbon Zero series, just to give you an idea. We introduced a courtyard into this design. The courtyard was set back enough from the front part of the dwelling so the light could come down over it, and we put the living there at the back facing onto a secluded courtyard. So the owners still get their private open space. The other thing, we've orientated that courtyard to east and sort of backed it onto that west sun in summer. East is generally a better direction. So north is the best. East is the second best generally in most of the southern colder parts of Australia, because you're trying to heat the home for a lot of the year during the winter and the side months. So if you can get the house heating up earlier in the day with east windows, that tends to make better temperatures within the house. So that's why east can generally be a better direction than west, even though they receive the same amount of sunlight. And there's just a 3D for you to get an idea of it. One thing I should say is when you put in these courtyards, from a thermal point of view, courtyards just introduce more wall area without necessarily introducing any more volume or floor area within the house. And from a thermal point of view, if you can minimize your wall area or surface area to the volume within the structure, then that's less surface area to gain and lose heat from. So it's a little bit more efficient to have an efficient shape, and cost efficient as well. Now, so if you do add a courtyard like we've done here, do it for a reason. We did it so we can get these high performance windows in, get that sunlight deep into the house. And on balance, it was a benefit for this design. This just shows you the connections between the spaces. All right, so that's the first rule. Simple rule, and it's simply try and get the sunlight into the living space for most of the day in winter, and then as many other rooms as you can get northern sunlight in, the better. All right, second rule, let the winter sun in and keep the summer sun out. So now that we've orientated the rooms right, now we're talking about windows and eaves, how much to put in and where. So window consideration is crucial to performance. I used to do literally thousands of ratings for other people, and the ones that fail are the ones that have too much glass and have it in the wrong directions. That's basically one of the biggest red flag issues that fail designs. And to give you an idea of how important it is to don't go overboard with glass, I do have that bubble there. It says, once you've insulated the house, up to 40% of the home's heating energy can be lost through windows, and up to 87% of the heat is gained through windows. So windows are very important, but effectively when the sun's not there, they become the thermal holes for the house. To put in some sort of perspective, the walls that you're seeing here, these external walls, say in that clerestory area, that'll be 90mm studs. We've got R2.7 bats in there. We've then got a reflective foil on the outside, a class 4 permeability version, facing onto an air gap. And then we've got, I think, EcoPly on the outside of this job. So there's maybe a half an R rating of reflective foil onto an air gap. And maybe over that whole wall, we're pushing around about an R3.5 for the wall. The glass, if that was single glazing, those windows would have an R value. If we converted window values to R values, they'd have an R value of about 0.2. 0.2 versus R3.5. So it's an order of magnitude less. Now, these are timber windows, they're double glazed, they're low E-coated, they're argon filled, pretty high performance windows. But even those only get to half an R rating compared to R3.5. So you don't want to go overboard with windows. So how much windows do you want and where should you place them? So there's two graphs that I'm showing you on this page that before I answer that particular question, I want to show you these two graphs because they're pretty interesting. They're for Melbourne, but they give a good idea of the value of north windows. And the graph on the left, if you look at that one, this is for a square meter of window in each elevation of the home, no eaves. And it's just looking at how much heat gain you get versus the heat loss. And then there's a dotted line that runs across that graph. And it says over on the right, Above that line, heat gain is greater than heat loss, and below that line, heat gain is less than heat loss. So if you're using single glazed windows, then only northwest, north, and northeast, those are the only directions where you're getting more energy in during the day than you're losing over a 24-hour period. But you'll also notice here over on left, it says heat loss range for high performance windows. If you start doing high performance, double glazed, low E coated, argon filled, you know, thermally broken or PVC or timber frames, you will very well find that your west windows will start performing for you and your east windows will start performing as a positive net benefit to the house. South windows typically are most of the time in shade and so losing energy, not getting that direct sunlight in to make up for it. So typically we'll just be putting in south windows for views, to pick up views, for daylighting into the rooms, and also for breezes to pull in breezes if the breeze path is going that direction. Over here on the right, we've got exactly the same setup of windows in walls with no eaves, 1 square meter, but this time that dotted line is a 2-bar radiator operating 3 hours a day. And this is what you don't want your windows to be for you in summer. And as you'd expect, south windows, that's got the less heat coming through it because the sun's on the other side of the house. Southeast is also pretty good. But then the next one is north, which is strange because we've just talked about putting our north windows in the sun all day. And this is without eaves, remember. The reason the north windows still perform well is that the sun is very high in the sky in summer. And so it's coming down, it's glancing off the north window, and a lot of it gets reflected, not so much goes through. Whereas on east and west, the sun is low and it's hitting blank on, you know, at a right angle onto the window and just going through in the east and the west. So a little bit about why north windows are so amazing. So what are the rules? Prioritize north, obviously. And then I've got here, go less than 25% of floor area. And what I mean by that is in any particular room, let's say the living area, let's say you've got 100 square meters of floor area of living space. You wouldn't want to have more than 25 square meters of window on that wall. That's 25% ratio. Can go up a little bit if there's some mass in the house, which I'll talk about later. But that's a good sort of ballpark to get your head in the game. Of course, the thermal performance software, the NatHERS software and an energy rater will be able to calculate exactly but if you're starting to push these sorts of numbers and higher, you definitely want to get a thermal performance assessor on board. For east windows, try to keep below 15% of floor area. For the west and the south, really we're trying to go to minimums for daylighting provisions on those sides. Now that's getting a little bit technical, trying to work out all these different rooms and percentages of glass. So I like to just have this rule of thumb. I just add up the whole house and say, okay, this house is 200 square meter home. And I'm looking at all the windows, I add up all the windows, and I just want to see whether I've got a ratio of 25% or less, and then I'm golden. So if I had 50 square meters of window and it's 200 square meter house, then pretty good. If it's going up above that, like I show down the bottom, like it says high performance windows and mass, less than 30% is probably okay. But if I'm going above that, then I might really want to say to clients, I think this is going a little bit high. I'm concerned that the house is not going to perform very well. I'm concerned that you're going to be uncomfortable. Let's send it off to a thermal performance assessor to have a look at it. I am a thermal performance assessor, so I would look at it. But for other designers and builders, that might be what you want to do if you're getting high square meter percentages of glass. All right, so that's basically how to lay out your glass, most in the north, a little bit to the east, less to the south and the west, and don't go over that 25% amount for total. Okay, how to choose windows for performance. There are 3 numbers that builders need to know, and designers and thermal performance assessors need to know about windows. One is the U value, one's the solar heat gain coefficient, and the other one is the air leakage. Now, I've done some posts on these, and if people don't follow the Builders Declare Instagram or Facebook, they probably should. I try and put out some useful information every now and again. I've hit 2 of those numbers. I haven't hit air leakage. That'll be coming up. Let me start with U value, because that is probably the most important. Now, U value is a measure of how much heat gets conducted through the window. And remember, we don't want a lot of heat to be conducted through those windows. This is not talking about how much sunlight gets through. This is about, if you've got a different temperature on either side, how much heat flow do you get across the window. We want our windows to be good insulators. Now, a U value is a measure of how well something conducts. So we want a low U value. We don't want a high one which says it conducts well. We want a low U value. And when you're talking about U values, it can get a little bit confusing, because the Australian windows are rated and tested under AFRC certification, Australian Fenestration Rating Council certification. And they will be testing the whole of the window. However, the U value of the window is made up of the U value of the glass, the U value of the frame, the U value of the spacer, if there's double glazing going on. All those things add together to a U value for a window. So just make sure that you're comparing, if you're ever comparing things, it is the U value for the whole window. And also, AFRC is not used, well, it's different rating protocols that are used overseas. And even if they have the same metric, sometimes you can look at European windows, for instance, and the U values look fantastic. It's because they have a different rating protocol, even though their rating metric is the same. So we have good windows here in Australia. There are some fantastic things overseas that we don't have, but I'm just warning you to make sure that you're comparing apples to apples when you're judging U values in different rating protocols. All right, what is a U value? I've gone on about it. If you have a look at this table on the side, let me explain it to you. We've got aluminium windows. They have a U value typically for a single glazed aluminium window. These are some typical values, 6.7 down to, if you go down to the best in this table, which is a timber window which is a more insulative frame with double glazed argon filled low E coated windows, we get down to an a U value there of 2. And what this means is that for every 1 square meter of window, if this 6.7 means if you have a 1 degree temperature difference between inside and outside, it's losing or gaining 6.7 watts of energy. Whereas down the bottom here, your double glazed version is only losing or gaining 2 watts of energy. So effectively, it's more than 3 times as efficient. So you're losing or gaining heat 3 times more slowly, which is what you want. So the rule is that throughout all of Australia, low U values are pretty much what you want. The lowest that you can afford within the price bracket for your house. So that's a matter of talking to different window companies, finding the price points and seeing, what you can get in a reasonably low U value. Anything between, anything 3 and lower is pretty good. I like to stay below 2 personally, but you can get good performance. We have no trouble getting to 7 stars with a U value of 3 or lower. Solar heat gain coefficient is a measure of how much sunlight actually gets through the glass. So this is measured between 0 and 1, 1 being 100% of the sunlight gets through, 0 being none of the sunlight gets through. A good value for single glazing is around about 0.6, 0.7 for single glazing, can get to those high values. But for a double glazed, low E coated, argon filled window, they usually have pretty chunky frames, and we're talking whole of window solar heat gains here. So you're looking more around the 0.4 or so. 0.4 or higher is pretty good value as a solar heat gain coefficient. Now, as you move up in latitude in Australia and it starts getting warmer, you may find that you don't want to have such a good solar heat gain coefficient. And that's where your thermal performance assessor, you should start talking to them about optimization, looking at tinting. Does that help? But in the southern states, we're trying to heat most of the year. We're really just wanting as much sunlight to come through those windows as we possibly can, as long as they're shaded in summer. And so that is what we need to look at next. How do we shade our windows? Well, by the way, air leakage, again, I don't have time to go over it today, and I don't have the relevant slide, but you're wanting a low air leakage number. And actually, if I just go back, I want to just point out this site, www.wers.net. You can go to wers.net. You can there's a database. You can rank by U value, and then you can even rank by solar heat gain coefficient. Find a window that meets your criteria, and then start checking the air leakage rates, which will also be in that database. All right, how to size northern eaves. So east, you can't really size with an eave because the sun rises, and so it's very low, and you just can't make an eave long enough to shade out the sun as it rises. Likewise, when the sun's setting, it's very hard to create an eave that will fix or to shade out when the sun is setting without also shading out the rest of the year. However, you can do so on the north because the Earth is on a tilt as it goes around the sun. The sun itself, as it travels east to west, is higher in the sky in summer, lower in the sky in winter. And there's a rule of thumb that works really well, for Southern Australia, pretty much up to Brisbane or so. This rule of thumb will work well. You can, of course, go better than this rule of thumb by modeling it in your software, and also when you get your thermal performance assessor to do an optimization rating at design concept stage, you could ask them about maybe playing with the eaves a little bit and seeing what it does. Some rooms are just a little bit cold, so it makes sense to pull them back a little bit from the ideal, or to put them out a little bit if they're overheating. However, what is the rule of thumb? This will put you in the right ballpark. And this is also something that a builder can check if you're just looking at plans. It's called the 45% rule, and it goes a little something like this. You just measure the distance from the sill to the underside of the eave. Whatever that distance is, h in this case, your eave should stick out by 45% of that, out to the gutter edge, if the gutter is the lowest point there. So if that height was, say, 2 meters, 45% of that, 900 millimeters. So that's how long that distance should be. The other thing that you'll notice is that the winter sun comes in at an angle, and so that means that at the top part of this window, if you increase the window to go all the way to the underside of the eave, that top part would never be performing for you. It would always be in shade. So if you want to maximize the performance of your glass, you pull down the head of the window by approximately a third of that distance, or 300 mils in this case. That's the 45% rule. If you are just putting on eaves over single windows, just make sure they run a little bit on either side by the depth of the eave, because the sun's not always directly in front. And I like to, when I'm looking at plans, I like to actually pretend that I am actually the sun, and I ask myself these questions. In winter, I'm in Melbourne, I'm at 30 degrees in winter. If I'm at 30 degrees and I'm rising in the east and then I'm setting in the west, can I see into all my windows? And can I see into the living areas for most of the day? That's what I'm asking myself. And then I'm imagining myself in summer. Summer, we're around about 75 degrees in Melbourne. And so I'm rising in the east, getting higher in the sky. Am I shaded out, especially at that midday when it's getting really hot? Are the eaves shading everything out, and then I'm setting again? So just pretend you're the elements and look at your elevations with that thought in mind. All right, so that's the second rule, and probably the most complex rule of them all, about how to place windows, how to size windows, and how to choose good performing windows, and how to shade out the summer sun, at least on the north where you put most of your windows. Rule 3 is keep the heat in and keep the heat out. So here we're talking about insulation, and insulation is actually really straightforward. What's hard is the installation of the insulation and getting that right. And that is something that builders declare bang on about a lot, which I've done talk about that I'll show you in a minute. I'm not going to go into it too much today, just a couple of points. The first thing is, for insulation to be effective, it needs to be complete. And one thing I'm showing here is if you don't already do it, you should be making sure that whatever you're putting on your external walls for insulation, that should run around the internal walls of the garage. Garages are notoriously leaky because of the garage doors, so treat them as outdoor spaces. And if you've got rooms above the garage, make sure you're insulating them as though they were an outdoor space. And don't do what I did on this particular design and put a sliding door into the garage space. They're very air leaky. It's really hard to seal a sliding door. So that was a silly idea. All right, what are the rules with bulk insulation and how much? Maybe I'll start with how much. This is a suggested starting point because, of course, the more insulation you can put in, the better. Sort of like water tanks. How big should my water tank be? Well, the bigger, the better. Then it can catch that downpour, right? However, we have space constraints. We also have monetary constraints. And you need to realize that there is a diminishing return on insulation thickness. So you get a lot of bang for your buck for your first R1 of insulation. You know, you might get half that for the next R1, half that again for the next R1. So it's not the same benefit each time you get it. What I've got over here are just some general provisions. This is what we use. R4 for the roof, R2.5 for the walls. We might push that to R2.7, but that's a bit more expensive. But we often do go to R2.7. Will also fit into a 90mm cavity. And underfloor, if we've got a subfloor, we'll go in R2.5. Now, using that, and we might put a reflective foil blanket over the top of that. So total roof might be an pushing more of an R6. But we use that specification, whether it's 7 stars, 8 stars, or 9 stars. It's all the same specification. It's not a matter that you need to upgrade and keep increasing the insulation. No, you've got to work with these other tools and get the design right. So that's just somewhere to start. And of course, you can ask the thermal performance assessor when you get that design rating done, you know, would more insulation, is there extra space? Would more insulation help? And you can look at, and you ask your builder about the costs of going to different insulation levels. Okay, the rules. These are just the basic rules. No gaps, 5% of holes equals 50% reduction or thereabouts in, well, it's in roof insulation in particular, but the point is don't have holes in your insulation. And if you look at this particular picture, you can see the stud work down the middle, and you can see it's nicely filled down between where there's a stud missing in those jam studs. This would be pretty rare to see on many building sites. We just leave that out. And of course, that adds up to a pretty big area of no insulation. So just be consistent. No compression. Now, no compression is a hard one, especially in standard construction, because you've got pipes, you've got wires and things going everywhere. If bats compress a little bit here and there, no big deal. A little bit of a decrease in performance, but it's not going to ruin the performance of the house. If it's everywhere and consistently compressed and squashed, yeah, that's not good. Try and limit it as much as you can. Overlap insulation at junctions. Beware of this, because if the installer is trying to get out of there as soon as possible, they might put insulation in the wall and just stop it a little bit short of the top plate. They might put insulation in the ceiling and stop it a little bit short of the top plate. And then you'll have a ring of uninsulated junction between the wall and the top plate all the way around the house, which won't do any favors when you're trying to heat and cool. So all junctions between walls and walls and ceilings need to have their insulation lapped. Flush with studs. These bats are notoriously, can be in standard construction. Yeah, I can put my face up to those and I can, you know, breathe through them. So if you've got gaps and cracks, you can potentially get air coming through. So you want to have your insulation tight up hard against the back of the plaster. Air or warm air come and go down between the gap between the insulation and the plasterboard. So you want to have flush bulk insulation when you're putting bulk insulation in standard construction. And of course, minimize thermal bridging. In the upcoming version of the NCC, they are planning to put detailed thermal break requirements for steel frames to make them comparable to timber frames, but they're not yet doing anything about structural steel in timber frames. So if between 500 and 1,000 times more conductive than timber, and that thing will just be radiating heat away at night on a cold night, or gaining heat for you on a hot day. So you want to really try and minimize thermal bridging. Or if you've got very high slab sides and you don't have any slab edge insulation, you'll find that the heat from your floor will just zoom out the side. So minimize thermal bridging. Now, I'm not going to go through oh yes, just a little note for myself. Have I checked the thermal bridging on my structure? And I always ask this question when I get my engineering. Is there steel going from the inside to the outside? Check the working drawings. If I've got a slab and it's got a high freeboard on the side of the slabs, well, once that gets over about 200 mil of exposed slab edge, oh, and do I know how to build tight? That's a question you should be asking yourselves, because like I said, standard batt insulation, it does not stop air infiltration. You need to know how to do membranes well on the outside of your house, how to make that nice and tight. And then on the inside, if you're going the passive house route, how to do membranes. If you're going standard construction route, you know, how to at least try and minimize air leakage coming through by working with your plaster to make that the tight element on the inside of the house, with a lot of caulking and yeah, sealing and penetrations. But I won't go into that today because that's a whole nother topic, and I've already done a talk on it called What Makes and What Breaks a High Performance Home. So if you check out the Builders Declare YouTube channel, I'm pretty sure it's up there. Also on Facebook and Instagram. So you can check that. One thing I will point out is if you're in cool zones like Melbourne, typically you might find that you can pick up half a star by insulating underneath the slab. I just want to say for the record too, you don't necessarily need to go for slabs. I'm going to talk about thermal mass in a minute, but there's no reason why a timber floored house won't get to 7 stars easily, right? So you can go timber floor, no problem. If you want to get 8, 9 or higher stars, maybe not even 8, maybe 9 or 10 stars, maybe then you want to start really thinking about making sure you've got a bit of mass in there. However, if you are going for a slab, and slabs tend to perform a little bit better in cooler climates, especially if you get some northern windows on with sunlight going onto it. If you are putting in a slab, some insulation under it will often give you a bump in your star rating. So I would always check this with my TPA. If you're doing a slab on ground, it's very quick for them to just put a bit of insulation underneath and they'll let you know how that performs. Now, you can put full insulation underneath, that's the best. Waffle slab construction over the top gives you a bit of insulation as well, so is not a bad from a cost-effective point of view. As you move up in Australia and you head up towards Sydney, you'll find that putting some insulation under the slab isn't so good for you, because putting in this insulation under the slab makes it easier to heat in winter, but you don't get as good a cooling benefit in summer. It's still pretty good down in Victoria, but as you need more cooling, as you go up in the latitude, up Australia, it becomes more important, the cooling function of the slab, and in those instances, it's better to get rid of the insulation and go direct slab on ground. And then as you go even higher up into the tropics and the ground temperature gets hotter again, that if you want to put a slab in then, I would definitely be thinking about putting some insulation under. The best way to know, check it with your thermal performance assessor. All right, let's get in. This is the 4th rule. So that's keep the heat in, keep the heat out, do your insulation well, build tight. The next rule is thermal mass. Store the warmth in winter and keep the cool in summer. So the way I like to think about thermal mass for me, and sunlight coming in and going on to the thermal mass, to me is a little bit like a glass and water coming in. Now, if I've got a lightweight home, I've got my glass, I've got my sunlight coming through the windows because I've put my windows on the north, you know, I've done the right sort of set out, sun streaming in winter, what will happen is the house will heat up, or that glass will fill up, and it'll get to a certain level where the water overflows and you can't store any more heat. And once the sun goes down, that water will start to sort of drain out of the glass. There's only so much in there. Now, putting in thermal mass is a bit like changing that glass into a bucket, or changing that bucket into a bathtub, or changing that bathtub into a pool, for instance. So thermal mass can be your friend if you've got northern sunlight coming in. There's two ways that, that mass works. First of all, mass works if you've got a big change in temperature throughout the day, what they call a diurnal temperature, large diurnal temperature range. But if you've got a large temperature range over the day, on average, you'll find if you put a bit of mass in the house, it takes a bit to heat the house up. The temperature can be going up and down a lot outside, but like I said, it takes a lot to heat it up. So the house heats up slowly inside, and then when it cools down outside, it will slowly go down. This graph on the left, the black is a heavyweight home. The green is the outdoor temperature. The dotted line is a weatherboard house. This is in Melbourne, and the weatherboard house, low mass. And so as the sun goes up, it gets out and the sun comes out, that house will heat up quickly. But then once the sun goes down, the house will cool down quickly, whereas the high mass home takes a lot more to heat up. And because this is during summer, this particular graph, that's actually quite a nice thing to be in that particular high mass home. Over here, we've got the winter version. We've got the green showing the outdoor temperature. Now, both of the houses are considerably above the outdoor temperature, so I can see it's getting a bit of solar gain. And both do pretty well when the sun is out. The lightweight home probably does a little bit better when the sun's out, but as soon as the sun goes away, the lightweight home cools down quickly and maybe goes into an uncomfortable temperature territory, whereas the heavyweight home performs a little bit better. So in places where you've got a high diurnal temperature range, mass will be your friend. In the desert, mass is your friend. Near the coast, in some of the more tropical climates, there's not much temperature difference, so mass doesn't have that benefit. You can, of course, turbocharge your mass by making sure you've got northern windows and you've designed the eaves. If we look at this first picture, you've designed the eaves so the winter sun can come in under them, can heat up the mass, and then when the sun goes down, the slab in this case is nice and warm. It will then radiate out into the internal environment, keeping the temperatures high, decreasing the need for space conditioning to come on to make up the difference until maybe the wee hours of the morning. Over in this, there's the summer instance. This time the eave stops the summer sun from coming in. But of course, heat will make its way, no matter how well you insulate, no matter how well you seal the house. Packets of heat will eventually make their way through over a long heat spell. But each packet of heat takes a lot of those packets to heat up a high mass home. So you'll get a number of days where it's cool before it becomes too hot. How much internal mass and where is often the question I get. So like I said, you don't necessarily need any to get to 7 stars, but if you want to get there a little bit easier, a slab on ground, well, a slab tends to be the most cost-effective way to spread mass evenly throughout the house. Now, this, the one you're looking at here, this is one of our 9-star homes. We had a lot of internal mass in this house in the form of brick walls, internal brick walls, primarily because the upper floor was overheating a bit and we wanted to get a bit of mass up there to lower the temperature a little bit on average. But if you're going to do this strategy, I would definitely say that you should be checking with TPA because you want to make sure it's cost effective. You want to make sure you're getting bang for your buck and it's making sense for you. The other thing you want to consider over on the wall here, a little sign, consider embodied carbon. You can quite easily find that the extra mass that you put into the home, the amount of energy that's gone into creating those products in that mass, be it the cement in the concrete or be it firing a brick, may very well be more than the operational savings you get over the life of the house. depending on the products that you choose. Here we've chosen recycled brick, so very low in embodied carbon. Obviously, the mortar is cement replaced mortar. The concrete is 60% cement replaced fly ash. At the moment, I'm doing a series. In fact, if you check out our Instagram or Facebook, I'm doing a series called the Embodied Carbon series, and looking at a lot of different strategies to really lower the embodied carbon in a home. But anyway, just keep that in mind and check with a TPA before adding it to internal walls. If you do add mass though, or if you even with the slab, in fact, our Carbon Zero series just have slabs. They don't have any internal mass on the walls. But if you go the all electric route, if you put photovoltaics on the roof and you've got an efficient reverse cycle air conditioner, you can start thinking of your home as a bit of a battery, because you'll be making a thermal battery, that is, you'll be making lots of energy during the day when the sun's out. And say during winter's good sunny day, you can actually turn the heaters on, you'll be making heaps of power. You can start heating up, in this case, the bricks on the wall and the slab in the floor. And similarly, as soon as the sun goes down, turn it off. Your good insulation around the outside of that thermal mass and high quality windows that you put in will hold that heat within the house, and you won't need to do the heating at night time. And likewise in summer, you'll be making heaps of power during the day, use it to run the aircon. As soon as the sun goes down, turn it off, it'll be nice and cool. So it combines really well, the all electric home with a bit of mass. All right, rule number 5, and this is the last rule, the last finger on your hand. Harness the breeze to keep you cool. And it's simply just to look at where the breeze is blowing on a summer's afternoon at wherever you're designing or wherever the house is going to be, and try and make sure that there are breeze paths that blow through your house in the direction of the prevailing breezes. What you're looking at here is my particular windroses. This is for Melbourne. In the morning of a summer, this is a 2 summer windroses. This is 9 a.m. in the morning. In 9 a.m. you can see that the wind is blowing here and there, different directions. But by 3 p.m. we're lucky enough to get a prevailing sea breeze that comes through. And actually a lot of suburbs in a lot of the capital cities will get sea breezes. So you should probably be thinking in your design about aligning to those breezes. And if you don't already know where the breezes blow in summer in the place where you're designing, ask neighbours, or you can go to the Bureau of Meteorology, look up this web link, and you can find the local weather station and get the windroses from there. Designing a breeze path is super easy. It's simply just trying to have a window or an opening on either side of the direction that the wind flows, and not to make it too complicated a route. So these are all just pictures that give that information, so I don't really need to say any more. Casement windows can be really useful if they open out. If you hinge them to the prevailing summer breeze, they will scoop it in if it's going down the side of the house. So windows on the side of the house, hinge them towards prevailing summer breezes. And there's just a schematic showing breeze paths through a house we did, showing how it can blow over the living spaces in summer, which is primarily where people are hanging out, where you'd like, when the wind's just right, you can open the doors and let that blow through. There's the same house in 3D. And once again, I like to be, just like I like to be the sun when I'm looking at my elevations, I like to be the wind when I'm looking at my floor plans and elevations. And I just ask myself this question: is it easy to get in and out in the direction that I want to travel in summer? And am I blowing across where people are going to be? Simple questions. And of course, don't forget, ceiling fans are still a very energy efficient way of moving heat and giving you a cooling feeling as it blows air across your skin and evaporates moisture off your skin. You get a 3-degree cooling effect. All right, that is the rules. You are now all, well, you're all masters at passive solar design. If you take in what I've said, you should find that your designs will, sit within that 7+ ballpark if you're meeting most of those rules that I just went through. You don't need to calculate it, because that's what the NatHERS tool does. You just need to know the logic of it as you're laying things out. Now, I would still say, though, that it's super valuable. This is my very last point. Super valuable to use NatHERS as it was designed, and that is as a design tool. It's become a compliance tool for the industry, but when it was first designed, it was there for designers to improve their plans, or at least that was one of its focuses. And I find, even though, you know, Chi, who designs for us, knows Passive Soul design like the back of her hand, she'll then do a great design. She'll pass it to me, even though she's been doing it for almost 20 years. I can get that design and going round the house. And by going around the house, I mean, I look at each room in turn, and the NatHERS software actually zones up each room of the house. And you input all the data about what the house is made of, what the walls are made of, how big the eaves are, any overshadowing outside, what sort of insulation, what sort of glass, put all that information. You then call up the local weather file for that particular climate zone, and it has data for every half an hour for a whole year. And you put that in, you press calculate, it'll then simulate the sun rising and setting, the breeze blowing, humidity, everything. And then it will work out what temperatures are in the different rooms, and then how much extra energy needs to go into those different rooms to bring them up to a comfortable temperature. And then it will look at that energy load and it will just put it into a star band. That's how the software works. But what you can do with it is you can straight away see, you know, one bedroom's doing well, but the other bedroom's not doing well. What's going on in this bedroom that's not going on in that bedroom? And you can start to play with the variables. You know, should the window be a bit bigger? Should it be a bit smaller? Should I pull the eave in or out? Is it overheating? Is there a tree outside? I should trim some of those bottom branches off to get the sunlight coming under. Is maybe that's if I need more sun. Sorry, if it's cool. If it's overheating, I'd be putting in or considering maybe I can make an internal brick wall in here to give it a little bit of mass and make it a little bit harder for that room to heat up too quickly. So that process, you can quite easily find half an extra star. So it is definitely worthwhile when the design is at design concept stage to farm it out to a thermal performance assessor and just establish a relationship. So the thermal performance assessor, you put on the information on the plan that thermal performance assessor wants to see, and that things go smoothly. So really important step. And we sort of break it down as to how much energy is going into the different areas, how much per square meter, and I can straight away see, you know, over on here, this rumpus TV area, that's using a lot of energy per square meter for heating. You know, what's going on there that's not going on in the dining area, that sort of thing. Thermal performance assessors can even run the building in what they call free run mode, where they turn off heating and cooling and see what the predicted temperatures are likely to be in the different rooms. This is a beautiful graph if you're a thermal performance assessor. To see this is without heating and cooling on. It's the outdoor temperature in blue is doing whatever it does, but inside, you know, we're maintaining that 20 to 24 or so throughout the middle of winter. In summer, it's going a little bit hot, but I've got my aircon, I've got my my solar panels, that'll be no trouble at all. And even if it starts to dropping down a little bit in winter, again, the technology we've got these days can make up for that. So still a very worthwhile process to do, and will definitely get you into the high star ratings if you do that. So we've arrived at the end. High performance living. Well, not quite, of course. We know that it depends on the build quality, as I mentioned before. And what we have done is really just got to this 7 stars, or, you know, 8 stars, 9 stars, 10 stars, but we've only really affected this space conditioning wedge. Remember, there's lots of other wedges to go, and that's where whole of home is really important. Unfortunately, I don't have time to go through how to minimize each of those wedges. Good news is I've already done a talk on it. It's maybe a little bit dated now. I'll give you all the information that you need to know. Perhaps when the rules come out of what's actually going to go into whole of home, we'll bring up an updated version of that. But this will definitely put you in the right ballpark of how to minimize and choose appliances to minimize the energy loads in each one of those other wedges, and also how much solar panels you would need to put on the roof to break even. But of course, the new whole of home tools will help you to calculate that as well. Whoops. And very last and slightly cheesy slide. Climate change is here now, but so are we. As you saw before from that graph, 39% of the carbon dioxide is related to the building industry, but that gives us the opportunity to roll up our sleeves and really make a disproportionate impact on that curve, on flattening the carbon curve. So climate change is here, but so are you, and you can make a difference, and the way that you proceed with your business will make a big difference. This is a challenge for humanity. Let's get on board. All right, Mike, that's my last push there. Back to you.
Thank you, Jeremy. That was incredibly detailed and thorough. And I think the way you broke that up into 5 different major areas was quite clever and quite easy to digest. So thank you. That was really informative. Even as a sustainable builder myself, I got a lot out of that. We've got quite a few questions. I feel like we probably might not have time to get through all of them. So I might pick a few. We might also send a bit of an email out with some of the questions that might require a little bit more of an in-depth answer. We had a question from Greg early on, which was sent quite early in the piece at 5:07. If you're approached to quote on a pre-designed extension or renovation, what are the ways you suggest improving the thermal performance to meet a 7-star requirement? Greg, I'm hoping that between 5:07 and 6:26, Jeremy actually answered that during this webinar. But if you need any further information, please reach out to us and let us know. But I'm hoping you actually got that answer you were looking for while you were watching. We've got a question.
Can I just make, I will just make one comment. And this is why it's really important for builders to know, because when they're quoting on these jobs, you don't want to be spending, it can take a long time to do a quote properly, as you'll know, Michael, and you don't want to spend your week quoting on a job that's going to have to go back to the designer. So that's why the building industry is going to need to change the way they do things. I would suggest that all designs in the future really start needing to have a 2-part thermal performance assessment, one at the design concept stage to tweak it and to improve it, and then you'll still need the compliance one at the end. So I'll go back to the assessor, they'll note any changes down and just do a compliance rating. And if you are a thermal performance assessor, you should probably start working out price scheduling for how you're going to run an improvement report type product.
Great point. And I know some designers are already doing that, and I think it's a really good process. So good comment there, Jeremy. We've got a question, Jeremy, what kind of transition period are we to expect? Will it be all at the discretion of the surveyor, like the example, or what if it's a project in the pipeline? So how long do you think we'll need to comply with this in terms of this change of policy? It's obviously also still in the works in terms of these changes that are being brought in, isn't it? Like, it's not actually settled just yet.
Yeah, let me get my crystal ball out here. Look, who knows? I'm hoping that sense will prevail. Anything in the pipeworks, I would say, should get a free pass. But who knows? I'm just saying that off the top of my head. And like I said, I'd expect at least a 12-month transition zone. I know that master builders and HA are pushing for at least, I think, 3 years, perhaps. And as long as we get on board with it, I don't mind if there's a transition period, as long as people realise that they're going to have to use that transition period to get up to speed with the process. And also understand it is going to be rocky. Like, it's going to be a bit bumpy trying to get this information about appliances and getting your head around that, getting the right information on plans. And then what if you change your appliance down the track? Are you going to have to go back to the building to the thermal performance assessment and get it re-rated? Possibly. So we all await what's coming down the track in September, and no doubt we will need to do some other presentation about what the actual rules are and what they mean.
If history is anything to go off, builders will have ample time to meet minimum standards. I'm sure of that. Another question we've got is recommended window type for climate zone 7, ? Aluminium condensation, ? That might be bit of a specific one. Jeremy, any thoughts on that?
Well, I'd try and stay away from non-thermally broken aluminium windows if you're in a cool climate, because you will get condensation on the frame. Even if you put in high performance glazing, you won't get on the glazing, but you might get it on the frame. So clad might be a better solution for you if you like the aluminium look on the outside, timber on the inside, or thermally broken aluminium might be better. But the U values on windows is a whole of window U value, and usually if you're getting down to those below 3s, you're probably starting to move away from aluminium as a framing material, or non-thermally broken aluminium anyway.
I've got an interesting question here from Ross. We often come across plans that have a deemed to satisfy energy rating with no star rating. How is this loophole compliant, and will this be regulated in the future?
Deemed to satisfy rating. So there are a few. You should listen to Builders Yak and the last episode, because they had Jessica Allen, I think it was, and she went over the different pathways. They talked about all the different pathways to comply with the code. There are other pathways than the NatHERS one. But yes, there are issues in the industry of compliance, and there's also issues obviously in build quality and meeting the standards. So a lot of things for the industry to work on. I'd have to look at that particular case to know exactly how to answer it.
Yeah, I think energy rater registration is probably a thing there as well.
Oh yeah, can I just say yes? You should definitely always use a registered or an accredited energy rater. That will be one that's either using Design Matters, or there are a few other accrediting, what they call AAOs. But just check that they're accredited. If they're not accredited, I'd be steering away from them, because you don't know that you're getting good quality.
Great. We had a question from Aaron, which was, if you were to compare a 6-star project home to a 7-star project home, what would be the key differences?
The key difference might be that the fully enclosed undercover alfresco courtyard with the outdoor infrared heating, probably not a good idea to try and get that to 7 stars. Look, it's exactly what I've gone over today. Just not too much, not too much glass facing the wrong way. Now, project homes have a little bit of an issue because they don't know what orientation that they're going to be. So I would suggest for all project homes, if you want to have a plan that's going to be in different orientations, don't go for 7 stars. Go for at least 7.5, if not 8 stars. Once you get to 8 stars, you can rotate that in any direction, and it will, it'll still be over 7 stars. So make sure you've got a bit of a buffer if you're a project home person. Yep.
Such a simple point, but a really important one was the importance of orientation. And Jeremy, it was really interesting that you were saying, without really doing anything all that groundbreaking in terms of insulation, like insulating really well, when that design for a well-orientated house is done properly, you can actually achieve quite a high star rating, without doing anything that out of the ordinary other than designing really well. So that was an interesting takeaway for me. We've also got general question: how do we design for a future climate? Was from Greg.
That's a pretty good question. There's actually the climate files. There is a future climate file pack that a thermal performance assessor can load into the tools these days. And you can look at different scenarios and how the house would perform under different climate scenarios. The good news for most of Southern Australia is that overall, you'll find that because we're trying to heat our homes for most of the year, as the temperature rises a little bit, you actually use a bit less energy over the whole year to heat the home. The hard part then will be that you'll have more of these extreme days in summer. And so then you'll be wanting to really consider, how you're going to cope with those. But once again, if you go all electric, maybe we'll have a little bit of mass, have a good efficient reverse cycle air conditioner and some photovoltaics on the roof, especially in the future when we get vehicle to home technology or vehicle to grid technology, where the car itself can become the battery for the house. even in outages, you'll have a huge battery there sitting in the car that can run the house for an extended period and give you quite good resilience from an all-electric home. So yeah, that's my take on what will happen under climate scenarios. Of course, once you get up into the tropics, that's just going to become hotter and more, more problematic. So good in the south, not so good in the north.
Really good question from Jared. Is there any way to prove your build has met the star rating once completed? At the moment, it's all based on the builders doing the right construction. Something we touched on a little bit.
Yeah, so I would do two things. I would take a leaf, like I said, I'd take a leaf out of the Passive House playbook there, and I would not wait. I wouldn't wait for legislation to come in requiring blower-door tests. I'd be starting doing it myself. You don't need to do it on every job, by the way. Typically, we will just do a blower-door test whenever we change, well, either if the client wants it, we'll do it, or if we're changing the type of build that we do, I'll do it just to get some feedback, and maybe every now and again I'll do it just to teach the team. Maybe we've got a new team member coming in, we use it as a team bonding exercise. That helps. That's one way to sort of say at least my house is tight, so I've met the tightness criteria. Taking insulation photos before the plaster goes on, really important, not only so that later on if there's a leak in the plumbing, you can find it in the photos. Well, actually that's before the insulation goes in, but taking photos of the insulation installed, again, that's proof I have done it. Apart from that, the only other way is to talk to the clients afterwards and find out how the house is going and see whether the house is performing. To give you a little bit of perspective, I spoke to the clients on that house that I put through the whole of house tool. That's been going almost a year now. They've got a new baby, and I know that they stuck in an inefficient dryer, which the client says that they run all the time. And instead of being 3 tons in positive, it's more like 1 and a bit tons in positive, but that's with a new child and washing nappies all the time. So yeah, that gives you, anyway, talk to, the owners will tell you how the house is going, no doubt. Those would be my tips. But yes, you want to start covering yourself, because if something doesn't, if you talk to the owners and there's a problem, well, you want to have that proof that you've done your job. You can point your finger up the line potentially to the designer in that case. And also you should be letting owners know that the house energy rating does depend on the weather in any particular year. They're using 30 years of past weather data. That's great, but the weather can change, and also the way that people use the homes can change. So it's worthwhile having, from a risk management point of view, having a handover manual. In that handover manual, just letting them know that the appliances that they choose, if they choose a huge screen TV that's like a 1 star, that's going to use a heap of power. So you can put those provisos in your handover manual just about the performance of the house. Can help cover your risk.
Brian's asked, is it up to the certifiers / energy efficient calculators to ensure this is now part of the process? And how can we ensure it's completed correctly? I think how we can ensure it's completed correctly was answered in the last question. But whose responsibility is it? Is it the energy certifier? Is it the builder? Who takes responsibility? Is it everyone?
I think it's going to be everyone. I would love it to be a certain person. I'd love it to be the building surveyor and pay them one more call out fee, perhaps. I know that the proposal is that the new rating will have a tick sheet at the back that various different people, the builder, the thermal performance assessor, I think the building surveyor, they all have to tick. Each one of the items on the list has been done. So it's sort of like a thermal performance passport, I think they're calling it. Yeah, and we will see. That's where policy and getting that right is just as important as having a tool that works. So yeah, we will see. I don't know.
Tim had a couple of comments about gas. We obviously generally promote all electric homes for the obvious reason that we can use solar to rebate that and also reduce gas usage. I guess on that note, Jeremy, probably a question from myself actually. Can you envisage in the future any sort of mandate for all electric homes or reducing gas on the horizon?
Who knows? We've had a change of government, maybe.
Yep. You never know.
You never know. I would have said no under the past government. Maybe they will. Look, I think gas will just fritter away anyway, unless it's really supported by government. It's just not going to make any sense. First of all, if you get rid of if you go an induction cooktop, they're cost effective now. Just as a good one of those is the same price as a good one of gas cooktop. That's usually the last electric appliance in the house. If you've gone heat pump, hot water, heat pump, air conditioner, then you can get rid of the gas meter. You save all that money. You've only got one bill. You don't have to try and work out megajoules and kilowatt hours and see how much energy is my house using. It's much simpler. And of course, once we get electric car charging as well, everything is just pointing the way of let's go all electric. So yeah, I think that gas has sort of had its day anyway, but we'll see. Obviously, if they hang around at some point, we need to say enough is enough. And I'd agree, Tim. I'd love to be able to say that at the moment, but let's watch this space.
From a sustainability point, it certainly stacks up going all electric, but also from an economical point of view as well. Paul's got a question. Thanks for the nice comment there, Paul. What sort of NatHERS performance should you target if you're aiming to build a net zero home on a whole of home basis? Will 7 stars do it? I think you had an example that was showing 7 stars as being net zero at the start of your talk, didn't you, Jeremy?
Yep, correct. 7.2 will do it. And look, I find with our homes, if our homes are anything to go by, we're down in Victoria, so it might be different in different states. But if we get to at least 7 stars, now we're sometimes into 8 stars, but even 7 stars, if we put in efficient appliances, we find that most homes start to break even by putting on a solar panel system size from about 5 kilowatts onwards. So 5 or 6 kilowatts seems to be sort of the break-even point for most families if you've done everything else right as far as appliance selection and you've got to that 7-star criteria. So yes, I think 7 stars is enough to go net zero for the industry.
Sort of great to know that it's not that far away to reach net zero at 7 stars as well. It doesn't seem like such a chasm. Tim had a question about why not shield the east in summer as well as west. Heat in morning or afternoon? I think that was about the orientation slide.
Yeah, yes. Good pickup. You'll probably notice on the slide that I was talking about, I think it was the one with the courtyard home. The sun rises there in the southeast, so it's not right from the start of the day. It gets a bit shielded from the back of the house in summer. But in winter, it's more coming in from the northeast, so it'll be shining right from when it rises. But yes, definitely put on some blinds. But we're in Melbourne, at least, we're in a position that we're trying to heat for most of the year. So you'll still get, from a thermal NatHERS star rating point of view, you'll get more bang for your buck having your east windows there, even though in summer, you should probably shade them. For most of the year, you're heating if you're just trying to get over that 7-star line. Now, comfort, of course, is a slightly different thing. And in summer, it would be great to have some east shading, just some blinds that drop down. Good point. Well taken. Thanks, Tim. Thanks for those curly questions.
And our last question from Greg. Thanks for the good questions, Greg. How much for a standard below a door test? Jeremy is asking. How much does it cost?
About $600.
$600. Pretty good to know how tight you're building, I think.
Oh, look, and it's a great. I use them as days. I get anyone who's new to the team or any trades who haven't done it before. I'll say, come around. We'll have a bit of a fun day and make it a team bonding exercise. And that you'll often spend that much money on a team bonding exercise just having a big lunch together. So go for it.
Absolutely. Well, that's it. Look, sorry we've run a bit over time. There was obviously a lot in that webinar. If you're still here, thanks for holding on. And Jeremy, thanks so much for providing such an in-depth webinar, which I think really covered it off very well. A quick note to anyone that's interested in it, there is actually a free training on this offered from Sustainability Victoria. If you go into the sustainability.vic.gov.au and go to the energy efficiency area, there is actually free training for both construction and also design, so you can sign up to that if you're interested. I'd like to say another big thank you to Maxa Design for sponsoring, and I'd like to thank everyone who came along, and we hope that this was valuable for you and you got something out of it. So thanks very much. And Jeremy, thank you again. That was really impressive.
Thank you everybody for coming. Thanks, Mike. And thanks, Max.
We will we'll post the recording up in due course. Thanks so much, everyone, and have a great night.